Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Vitali Halenka with us today. Hey, Vitali.
Hi, Francis. Thank you for having me.
Well, thank you for agreeing to talk about your very lovely article. It's a nice one. Vitali, where are you located at?
I'm actually right now in Ohio. So I'm actually doing research as independent researcher right now. So I started my work as grad student at University of Michigan. So I was working with my PhD advisor, Christopher Miller, on this work, as well as his undergrad student page, Monsicle. So, it was really good work, but now I'm keep doing research, but as independent researcher. So.
Okay. Very cool. Ohio is spring starting in Ohio? Is the ground defrosted? You got little buds?
Oh yeah, it is. So it's pretty warm, raining outside though. So not ideal weather, but not terrible.
It's not cold.
Yeah, summer is coming.
Good. Oh yes. So it is April 7th, 2022 as we shoot this, and I'm in Phoenix, and summer is right around the corner in Phoenix. We will probably hit 100 F tomorrow, next day. So we're going to start hitting the triple digits in F soon. So good and toasty. It'll be great. Vitali, what do you like to do for research?
Well, my research focuses on galaxy clusters, and the goal is to actually use galaxy clusters as a tool to test cosmology and gravitational models. And some of my research is actually focused on modified gravity models. So I did some work on emergent gravity, FR gravity, and stuff like that. So, I have combination of galaxy clusters and modified gravity together. So
it's a good combination. It's a nice testing combination. And that is going to bring us to this very awesome APJ article, open access these days, people. You can go get it. Quantifying the projected suppression of cluster escape velocity profiles. And Vitali, take us away.
All right, thank you. So first of all, I want to thank my collaborators, Christopher Miller and Paige Monsicle. So it was really nice working with them, and I keep working with them actually, but on the other projects. And so the goal of this paper, we focus on phase spaces of galaxy clusters. And probably if you can scroll down right away to the figure 1.
Let's go straight to figure 1.
Yes. So in here, you can see it's a phase space of galaxy cluster, and it is densely populated with some galaxies, as we call them, tracers. And it is projected view. So as if we see it from our perspective. And we escape. The dashed line is our three-dimensional escape velocity that we infer from weak lensing, as well as by using cosmological parameters in the lambda CDM model. However, because it's projected, we observe different line, which is our solid line. And the solid line is actually the maximum observed velocity. And unfortunately, it is lower. So we can't actually get the full three-dimensional escape velocity. So, and generally speaking, from observation as well as in-body simulations, it is approximately 60–80% to the underlying escape velocity.
Okay.
The question is, why do we care about escape velocity? And if you can move a little bit to the right, you can see equation 2. So we can see there is great connection between escape velocity and gravitational potential. And obviously, by using gravitational potential changes when we change gravity or cosmological parameters. So gravitational potential and specifically escape velocity profiles of galaxy clusters provide us with direct measure of gravitational potential that allows us to test all of that good stuff.
Got it.
So it's pretty cool. But unfortunately, as I just mentioned, we have projection effects and they suppress it. And if we would know the magnitude of the suppression, we can go back to the actual three-dimensional escape velocity and we can test gravity models, cosmological parameters, and as well as infer the underlying mass of galaxy clusters.
Right. Okay.
Yeah. So that's good. And obviously there was some initial work, and it was there are like two great papers, 1997, Diaferro and Geller in 1999. And what they proposed was to use velocity anisotropy as a way to go from maximum observed velocity profile and projection to the actual three-dimensional escape velocity.
Okay.
And this velocity anisotropy is a function of velocity dispersions. However, it has at least two problems. So first of all, this premise suffers from statistical issue that wasn't addressed before, actually. So to calculate dispersion, we would calculate everything along the line of sight. And so on the figure 2b, you can see kind of three different positions along line of sight: box C, box B, and box A. Okay. And when we would calculate along the line of sight, we would take them in account pretty much equally. However, our gravitational potential actually monotonically decreasing function. And so, generally speaking, velocities of our tracers in box A and C would be lower than box B. So that would create some underlying bias in our calculations. So it's not fully correct to do that. Moreover, if we specifically look at the box B, there is a chance that we can actually observe the full three-dimensional velocity, escape velocity, even in projected view. So if the galaxy or tracer has actual escape velocity, and it is on this particular place, like at approximately R perpendicular, and it points along the line of sight, we would actually be able to observe the full escape velocity even in projected view. Okay. However, based on Diaferro and Geller work, based on anisotropy, it is not possible. It is always suppressed. So what we say here is probably it's based on undersampling. So the more galaxies, the more tracers we would have, the higher chance of observe something like that. Because obviously, if we, having all these conditions satisfied at the same time is pretty unlikely. But the more galaxies, the more tracers we have, the chance increases. And so that's our idea, and we are going to test it in our paper. Okay. So to do that, we actually introduce what we call the suppression function. Okay. It is in the equation 12.
Let's do equation 12 on a suppression ratio. Okay.
Yes. And so what we do here, we pretty much just say the magnitude by which the actual three-dimensional escape velocity is suppressed when we look in projected. So V escape is our 3D escape velocity, and V escape LOS is our observed maximum observed velocity in projected view. So that's what we define, and that's what we focus pretty much the rest of our paper. So in order to test that, we use the action-based galaxy modeling architecture, or in short, AGAMA, and that was done by Vasilyev in his paper 2019. And what it allows us to do is actually to recreate the phase space of galaxy clusters based on some underlying parameters, like density, underlying cosmology, and number of tracers in a projected radial range. And that's what we actually do. So our interest, again, is our suppression function ZV. Everything else we want to vary, we want to test, but that's our goal, and that's what we do. So generally speaking, we don't, like, for example, as in observations, we would get our density distribution, let's say from shear measurements from weak lensing, and we can get our density. We know our cosmology, for example, like from Planck or the other observations, and that would allow us to kind of recreate the cluster. Obviously, it suffers some drawbacks, like we don't know fully dynamics, but in our work, we don't pay attention to the dynamics in our phase space, we focus explicitly on the edge. The edge is what we focus because it actually shows us the actual gravitational potential.
Right.
And so if you can scroll to the next, yeah, like here would be good. So like on this here in step 1, what we require is to have the cosmology, like energy density of dark energy, Hubble parameter, and we work in our paper in a flat universe specifically. Then we require some density parameters. So we work also like in spherical symmetrical systems, and we also require the number of galaxies in the projected phase space. We work explicitly in the area 0.3 R200 to R200 because in real observation systems, we have kind of undersampling issue in the core. So we explicitly try to focus our research in this area because, you know, beyond R200, there are not enough galaxies, and it's hard to kind of infer the escape profile. And in the core, there is also lack of data. So we try to focus on this range, and that's why we defined our number of galaxies in this range specifically. And so by having those parameters, we can recreate the cluster, but with specific parameters. Again, our goal is not to have same distribution in the middle. We want to get we want to get back our edge, and apparently we can do it successfully with our AGAMA software. And so if you can scroll to the next page, to the top figure, yes, that's good.
Very good.
So that's great. And unfortunately, on the left figure, as you can see, AGAMA has one issue, which is it doesn't have cosmology inbuilt. So we need to make a cut. What we do is, so here we have like simulated by AGAMA phase space, and the edge is actually the black line, the top line.
Right.
But because of presence of dark energy and because AGAMA doesn't include cosmology in it, we need to push it below, and all the galaxies that are above that line, we actually drop those.
Okay.
Yeah. So, and that phase space that is below red line, that's what we're going to use, because based on, excuse me, based on other data, approximately over 500 million years, the galaxies that sit above the escape line, they would, you know, kind of go away, fly away from the phase space, so they wouldn't interfere. Right. So in n-body simulations, it's actually not a problem, and that's kind of a trick that we came up with to actually use this great AGAMA simulation in our work. Nice. And because it has some like significant advantage, because we can change our cosmological parameters, we can change like anisotropy, masses pretty quickly without a need of running n-body simulations. Again, n-body simulations would be great if we would care about dynamics in the phase space, but we can, but since we presumably care only about the edge, it's not a big deal. So, and with n-body simulation, again, it's a lot of computational power, and we can't do as many, you know, steps in a grid as what we can do here. We can actually tailor everything to what we want based on those initial parameters. Cool. And so what we do actually, then we have this, based on these initial parameters, we have our AGAMA simulated clusters. And what we can do, we can look at them from various positions, as if we, you know, observe from different positions in the sky. And we do that like 30 times. Okay. And we run that on the figure 6, if you can scroll to the right.
There's our suppression factor. Okay.
Awesome. Yeah, so like pretty much we can, we do that based on millennium simulations. And based on that millennium simulation, that the black line is the underlying suppression. And based on AGAMA, we can again look at that cluster 30 different times from 30 different positions, and those like thin gray lines, those are individual suppressions,
yeah.
and taking the median is the blue line, and we can see pretty great agreement with underlying millennium results. So
Factor
pretty much, yeah. So pretty much a gamma framework allows us to systematically test the suppression function against the simulation, and does it in controlled environment where we can, have multiple realization of the same cluster. So we can not only look at different positions, but we run it multiple times. Like we create those like mock cluster multiple times as well. And yeah, that's pretty much the approach what we do.
Got it.
And we had other choices. So obviously to actually do that, we need some basic cluster parameters. Like we can't just take out of nowhere density, for example, right? We need some basic, and we have multiple choices, but we decided to use Millennium simulations for that. Okay. And they have like semi-analytic galaxies as well as particles, so we have a choice to what to do. Okay. And we use those, but again, I want to stress out that we are not fine-tune it specifically for Millennium simulations. Yeah. We use it as a kind of base to have kind of real looking systems. And later on, we see that they actually working. In a few, like later in the paper, we'll discuss that, but we test against other simulations, like dark sky simulation, for example, and we found that everything's working great. So it's not like, it's our choice. Millennium simulation actually allows us to do that. So it's all great. And so if you can scroll to the figure 7.
Let's take a look at figure 7.
Yeah. So what a gamma allows us, we can pretty much drop as many tracers as we want to. Again, we do it randomly. And so on the left figure, we have approximately like few hundred tracers. And what you can see here is like the dashed line is actually our observed maximum observed velocity profile, while the red line and while the green line is actually our 3D escape velocity profile, and the red line is as if we don't have dark energy in our universe. So you can see that dark energy, pushes our escape profile, kind of downwards. So it pretty much takes those galaxies that are above escape profile and pushes them away from the phase space. So they escape.
Yep.
But then if we do literally the same cluster and have 10,000 particles or 100,000 particles, we have our dashed line is significantly higher, and it's pretty much at the same, it pretty much covers our 3D escape velocity profile. So pretty much for 100,000 particles, we can recreate the actual escape velocity profile. Unfortunately, it's not what it happens in real universe, because we don't have as many galaxies in our galaxy clusters. Real systems that we observe currently, they have approximately from 50 to 500-ish galaxies, with a kind of median around 100. And so that's why kind of left figure has more representation of our reality, and that's why our observed profile edge is actually only like 60-80% to what it should have been, or what it is in reality for 3-dimensional escape profile. But from this figure, we can see that there is actually hint that we are going in the right direction. So, and then what we do next is actually, again, why we develop it is to test cosmology and to test massive galaxy clusters. So we need to test if it holds, if we vary cosmology, if we vary anisotropy, if we vary mass. Does our
robustness
suppression changes if we do that? And so that's what we do in our results section of this paper. And we start here, we do more thorough approach, every cluster that we simulate using a gamma software has almost 5,000 galaxies.
Okay.
And we do 100 views, not 30. Now it's 100 views. So we try to do as thorough approach as possible. And first of all, like here on the figure, on the left figure, we split our clusters into two subsample, like heavy clusters and less, 50 heaviest and 50 less heavy clusters. So like from Millennium simulations, I forgot to mention that before, we have 100 clusters that we use as a base for our gamma modeling. And so we split those into two bins. And what we can see here is actually a little bit difference. There is no like radial dependence, and the average difference in a range from 0.3 to R200 to R200 is approximately 2%. So which is not significant. And we think that it is due to the way we bin everything. So we use bins based on R200.
Okay.
And by doing that, we create a bias in the number of galaxies per bin. And so that might create a bias. We'll probably explore that in the future, but because the change is so small, it's pretty much less than 2%.
Yeah.
To be precise, like you can see this ratio, the bottom blue line.
Yep.
It is only 98.98, so it's like around 2% only below. So it's not significant difference, but yet we need to take it in account, as a systematic uncertainty when we actually test cosmology.
Yep.
So the next thing what we did is to look if it changes the change in cosmology. First, on this figure, we changed the energy density of dark energy. And as you can see, we went like wide range from 0.6 to 0.9 on this figure, which is far beyond what we actually observe. Right. But on the bottom figure, we did the ratio when we used like the range of our current observations.
Okay.
Using AAS and Planck collaboration data. Right. And what we found here that pretty much there is no difference. Like there is no radial dependence, no difference. So we can safely test cosmology, at least based on dark energy density of dark energy. Nice. On the right figure, we also tested Hubble parameter. And as you can see here, we also did like really wide range. So, but still we don't see any significant statistical difference. And when we look at the range of parameters that we currently observe, there is no significant difference as well. So we're good to go on this case. So pretty much our suppression doesn't depend on cosmology, or hence there is only slight dependence on mass. But then we need to go to our next figure 9, where we test anisotropy. As I mentioned before, the initial work by Diafer and Geller, they proposed to use anisotropy to actually see how much the projected maximum velocity is actually suppressed compared to an underlying 3D escape velocity. And what we can see here is actually we went really wide range. So from minus 0.5 to 0.5 in our anisotropy parameter. Right. And unfortunately, we see some radial dependence here. But since we work in a range from only like in in the range 0.3 to 1 R200, we can by taking average, we see that the change is pretty small. It is only like 0.5%. Yeah. So average is small, which is great. We still would probably need to take that into account. Yeah. But the most important part that the average suppression is pretty much 0. Again, we see the shape, but what we are going to use in our actually when we're going to test cosmology and gravitational models, we will take the average, and the average is pretty much 0. So we can safely work in this range from -0.2 to 0.5 and see pretty much no difference. Again, we chose these numbers on the bottom figure because that's the numbers that are currently in the literature. That's what was found by other researchers. So like while we use here beta -0.5, it's far beyond what is currently observed in simulations.
Okay.
So again, what we see here, the cosmology, in particular Hubble parameter, and the energy density of dark energy, as well as the mass and anisotropy don't play big role in change of our suppression function, which is great. So now we can safely move to see how much suppression function changes with the number of galaxies in our projected range.
Okay.
In other words, we're going to try to quantify our ZV function. And so that's what we actually did. And if you probably can scroll to the figure 10. So here on the left, that's like a gamma representation. We use our gamma and we plot our suppression as a different number of galaxies. And we can see really nice trend. The more galaxies we have in our phase space, the smaller suppression is, and the closer our observed maximum velocity profile to the actual underlying 3D escape velocity, which is great result. That's what we kind of, set as our hypothesis at the beginning, and that's what we actually see here. So but on the right figure, we use our underlying millennium simulations that we used as a kind of base for our parameters that we later used in the gamma. And in our millennium simulations, we see similar trend. The more galaxies we have, the lower suppression is. Yes. And what we decide to do, we introduce this like 1+ inverse power law, our suppression function here in formula 14. Yes. So pretty much would say the more galaxies and we have, the lower suppression is. And the closer we go to, like the bigger the number, the closer we go to 1. Yes. So which is actually what we saw before. I believe there was figure 7 when we had like 100,000 galaxies and we had like our observed velocity close to the underlying 3D escape velocity. Yep. So, and using our gamma, we've been able to find these parameters and 0 and lambda, and that's what we found. So that's the parameters of interest. So if someone decides to actually like test cosmology and someone has those like underlying galaxy clusters, he or she can measure the state profile, the projected maximum velocity profile. Using this formula, you can easily get back the underlying 3D escape velocity and start testing cosmology.
Yes.
So again, as I mentioned before, that's all great, but to kind of test it against some other simulations that we are not biased just because we use millennium simulations everywhere. We use dark sky simulations. Okay. And so, and we also split our data sample into 2 bins. So if you can scroll probably to the next figure. So like our green arrow bars, that's our dark sky simulations. Yep. And so the solid and dashed lines, the difference between them is like we had like 20 clusters and we split them on heavy and low mass systems. They actually on the same N, but to represent them correctly, we shift them slightly to the left. And so what we can see here, blue error band as well as error bars are from our gamma, red our millennium particles, and individual crosses are from millennium galaxies. So in millennium simulations, for those who are not familiar, we have particles, and also based on works, we can have analytical galaxies that were kind of put there afterwards, after simulations, kind of identified. And so those like small crosses are actually those when we use galaxies instead of particles. And we can see overall really great agreement between all of these individual individual results. And what we can extract from here, again, first of all, our suppression is highly dominant. To much higher degree compared to other parameters like cosmological parameters, mass, or anisotropy. And in particular, if you can scroll a bit to the right, what we compared here, we, instead of using 5,000 tracers as we did before, we actually looked at the range of our observed system, which is, again, in our observed systems, we usually have from 50 to 500 or like 40 to 600 galaxies, which means that we want to focus on those ranges specifically. And what we found here on the 1, 2, and 3, that the biggest difference in those ranges that we looked are pretty small. So it is only the maximum difference is only 2.7%, and moreover, in 2 out of 3 of these approaches, we haven't noticed any trend, which is really important. That it's probably we see the changes are due to statistical errors. It's not actually trend, and they actually don't play a big role in our suppression. So, which is really good sign. Obviously, we'll need to do some work to kind of improve our precision, because again, as I mentioned at the beginning of chat, that the biggest systematic uncertainty when we actually want to test cosmology using escape velocity profiles comes from this suppression. And the better we have, the higher precision of this suppression we have, the better our results are going to be. And so, again, the final conclusion is pretty much that cosmological parameters, mass, and isotropy can change our suppression only by maximum 2.7%, while the suppression change due to the number of galaxies is actually 36.5%, which is almost 14 times bigger. So again, we can simply use these 3, again, cosmological parameters, mass, and isotropy as underlying systematics, which is quite small, and use our suppression as the majority of contribution to our to the suppression. So again, n is the biggest factor here. And yeah, that's pretty much the summary of this work. So yeah.
Thank you. That's awesome. Yeah, Vitali, thank you for walking us through this very lovely APJ article. So you mentioned it a couple of times as we walked through. So I'll just push a little bit on that here. So where do you think we go, let's say, over the next 2 to 5 years? Are there additional simulation to be done to further show the robustness of it? Are there anticipations of applying it to observed galaxy clusters and so on? So just sort of where do we go over the next 2 to 5 years?
Sure. Again, I guess we can have 2 directions. First, kind of improve the precision and accuracy and test further. Again, like having some other simulations, and that would be great. Like one of the things that I think I forgot to mention, we still have the result that I showed in the last figure is the average suppression, but it would be nice. But we have some radial dependence on individual ZVs, so it would be nice to quantify that to improve the precision, because this way we can reduce our error bars, and yeah, just further test it. And the second is actually implement it, and that's what we actually already work in. That we have like we have significant progress in that. We collected quite a few galaxy clusters that we can utilize, and results look promising. So yeah, just implement that, have the more data the better, and then we can just provide quite nice tests to cosmology and gravity.
Yeah, yeah. Well, there's a number of surveys coming up here. Let's say over the next 5 years,
Yeah, like right now we just use pretty much data from literature. So we just collected all the these different catalogs. Again, we need like weak lensing data, and we need distribution of the galaxies, so we can build our phase space to inform our maximum projected escape profiles. But so we have available data sources. Right now, it's kind of messy in a sense that we need one robust system, one robust database to have the best results. But yeah, we definitely can already do some interesting results with that.
Nice, cool. Well, I look forward to seeing this develop over the next couple of years.
Yeah.
Very cool. Vitali, thank you once again for walking us through your very lovely article.
Sure, it was my pleasure. Thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.